The derivative is the foundation to all of calculus. In order to understand the derivative, let's first look at the behavior of the graph of a curve on the black axis. Let's say the curve starts out horizontally. It's neither moving upward nor downward. And now it starts to turn, and it's heading upward. We call this increasing. And it's defined as heading upward, always as we look from left to right. And now it turns and is more increasing, and yet more increasing, until it reaches a section where it maxes out how rapidly it is increasing. It is the most steeply upward as we move from left to right. Now it's going to start to turn, and while it is still increasing, it is less steep, and even less steep, and even less steep, until it becomes horizontal. And now it's going to turn and start heading downward as we move from left to right. This is called decreasing, and is defined as heading downward, always from left to right. And now it's going to become more steeply decreasing, and even more steeply, until we reach a section where it has a maximum decreasing steepness. It's now going to start to turn while it is still decreasing. It is becoming less and less steep, and less steep until it becomes horizontal, and now it's going to turn and start increasing once again. The derivative describes the behavior of a graph in each of its sections. It is a positive number for increasing, it is a negative number for decreasing, and it is a 0 for horizontal. The magnitude of the derivative tells you how steep it is in each of the locations. A larger magnitude positive number is more steeply increasing, a larger magnitude negative number is more steeply decreasing. The steepness of a curve is not something that we can directly measure. The only thing that we can directly measure the steepness of is the straight line. The steepness of a straight line is its slope. So in order to measure the steepness of a curve, we have to get creative, and we have to mimic the steepness of the curve by the steepness of a line. Let's look at an example. I'm going to go to the red axis, and I'm going to draw an example of a curve on the red axis. And let's give an x-coordinate to a point that's on the curve. Its corresponding y-coordinate will be the function evaluated at that x-coordinate, so that'll be f of x. And let's give a second x-coordinate to make it different from the first x-coordinate. Let's give it a value of x plus h, where h can be any number except 0. It can be a positive number, and x plus h will be to the right of x, or it can be a negative number, and x plus h will be to the left of x. We just don't want h to be a 0. Now let's draw the corresponding point on the curve above that x plus h. That'll be about right there. And that'll have coordinates of x plus h, and then the y-coordinate is found by plugging the x plus h into the f representing the function, and we get f of x plus h. Now we can draw a line connecting those 2 points. We always need 2 points to give the equation of a line and to find the slope of the line. This is known as the slope of the secant line. It's called a secant line because it's touching the curve at 2 points. The slope of a line is always found by taking the rise, which is the change in y-coordinates, over the run, which is the change in x-coordinates. We have to pick one of the 2 points to be the final point, and the other one will be the initial point. I'm going to pick the rightward point to be the final point and the leftward point to be the initial point, so that we can measure the delta y over delta x. Delta means final minus initial. For delta y, we want to take the final y-coordinate, that's the y-coordinate of the rightward point, and subtract from it the initial y-coordinate, that's the y-coordinate of the leftward point. And then we'll divide this by the final x-coordinate, that'll be the rightward point x-coordinate, x plus h, minus the initial x-coordinate, that's on the leftward point, which is x plus h minus x. The x's will cancel, and that will leave us with just an h. There's your slope of your secant line. The slope of the secant line does not mimic the curve very well. If you look at the steepness of the secant line, and you look at the points that it's connecting right here and right here, it does not mimic the steepness of the curve at either of those locations. The steepness at the leftward point is more like that way, and the steepness at the rightward point is more like that way. And it's not mimicking either of those. However, if we start to push the rightward point closer to the leftward point, it will start to mimic the steepness of the curve a little better. Let's say the rightward point were a little closer and it was here. And now the secant line will look like that. Now again, that's mimicking somewhat the steepness, but not quite. The steepness of the curve in the location of the leftward point is still steeper than that secant line. But we can push it even closer, and now it's starting to get better. If we draw a line through there, it's starting to mimic more and more the steepness of the curve right there. And the closer you put it, if you put it really close, it's going to mimic it even better. And now we're starting to have a slope of our line, which is the steepness of our line, mimic the steepness of the curve in that region. And it becomes better and better the closer those are together. Now, we cannot make those 2 points become a single point because we will no longer be able to describe the slope of a line, but we can make it become as close as possible without becoming exactly the same point. And that's going to be done by changing that h value. That h value is the distance between the x-coordinates. If you look here, one's x and one's x plus h, and the distance between them is h. While we can't make h equal to 0, we can make it approach to 0, and that's why we use a limit to describe the slope of the line as the 2 points get closer and closer and start to mimic the curve a little bit better. It's going to be called the slope of the tangent line. And it's described as dy over dx. We changed the deltas to become d's now, and that's because we are making h become really small, and the 2 points are going to be so close together they essentially become like a single point. And we have a really small change happening for the x and y. It's a small number over small number result. And it's found by taking the limit as we make h go to 0 so that we push the 2 points closer and closer together. Of that same expression of the secant slope, just taking the limit as h goes to 0. This is known as the definition of the derivative. Its result will give you a function that describes the steepness of the curve at every one of its sections, every one of its x-coordinate points. Now we can write another version of this where instead of using an x, we use an a, and what that will do is give us the steepness at a specific location. A is going to represent a specific location. A is a number. X is a variable. And it'll look the same, except we replace the x's with a's. And then there's yet one more way that we can write the steepness of a curve. I'm going to go now to the blue axis. And I'm going to draw a curve in there. And I'm going to pick out 2 points, one that'll have an x-coordinate of a, and one that'll have an x-coordinate of x. And to find the corresponding y-coordinate, we plug each of those respectively into f. So we will have a with f of a, and we will have x with f of x. And we can now draw a secant line passing through those two, and we can find its slope by doing the change in y over the change in x, or the rise of the run, final minus initial. I will make the rightward point be the final once again. So the change in the y-coordinates, final minus initial, over the change in the x-coordinates, final minus initial. There's your secant line. Now we can make this become a tangent line by having those become so close together they become essentially a single point by taking the limit, and it will then become, again, dy over dx, because we will have a very small change happening. And this will be accomplished by making x approach to a. And that pushes the rightward point closer and closer to the leftward point so that we can mimic the steepness of the curve. And that'll look like so. Now all three of these slope of tangent line equations I've written down are all used in calculus. The one that I have in the box is the original definition of the derivative. That is the one that will give you the function of x definition of the derivative. The other two will always give you a number, which will represent the slope of the tangent line at a single point, whereas the definition of the derivative gives you the slope of a tangent line anywhere, because it will become out to a function of x, which you then can plug any coordinate into and get the slope of the tangent line at that location. Remember, the slope of the tangent line is mimicking the slope of the curve. One more thing about these three slope of tangent line equations I have. If you look at each of them, look at the one in the box, the definition of the derivative. If h goes to 0, you get f of x minus f of x, which is 0 over 0. It's a 0 over 0 indeterminate form. If you look at the one below it and you have h going to 0 there, you get f of a minus f of a, which is 0 over 0. And if you look at the one in blue, slope of the tangent line, and you take x to go to a, you will have f of a minus f of a over a minus a. And that is, again, 0 over 0. All three of these give you the 0 over 0 indeterminate form. So when you make use of the definition of the derivative in any of its three forms, you will always have a 0 over 0 indeterminate form to begin with, and what you have to do is rework that 0 over 0 indeterminate form by methods described in the 0 over 0 indeterminate form limits, and that will give you the result that will be the slope of the tangent line, the derivative, and mimicking the steepness of the curve at that location. That is why we have the derivative with its definition.